We'll be learning about exponential growth and decay. So exponential growth and decay, the formulas for them come from the exponential equation or function. So that was y equals ab to the x power. So when we have a growth, we're going to still have that same y equals. We have the same a, but it's the b multiplier that looks a little bit different. And then also the exponent is t for time. So this is our time for our exponential growth. And the same amount, this is our final amount, is y. And we'll label that growth. So the b, the multiplier, to have something grow, it has to have a growth, what we call a growth factor. And that growth factor is written in a kind of a different way. So it's 1 plus the rate, the percentage rate. Oh, I forgot one more of these. This is our, well, it's our y-intercept if it's up here where x equals 0. So that in a growth, an exponential growth, is our initial amount. And that's the starting amount, meaning x equals 0. Or in this case for growth, t equals 0. So initial amount. So now that we have kind of all the pieces, let's take a look at that growth factor. That growth factor is this whole piece right inside the parentheses. So that is our growth factor. And how that is that rate is our percentage rate. So if we think about that as our rate is that the percentage rate. So if that's the percentage rate, this one is 100%. So to have a growth, you have to have 100% plus your rate, your percentage rate of increase. Now, you have to remember that this is in decimal form. And that's why our 100% looks like a 1. We've moved the decimal over 2 places, and it is a 1 for 100%. Now, when we look at decay, the equation is very similar in that it's a to the t power, this multiplier, but it's the 100% minus r, because to get a decay you have to subtract your rate of percent from the 100%. So if we take a look at our first example down here, now that we know this, the inaugural art festival attendance, inaugural, meaning first. So if it's the first, that means it's t equals 0. So that would be in that place of a, the initial amount. The attendance increases 10% a year. And we need to write an exponential function. So that means we're going to use the growth one. So I'm thinking of my formula, which is y equals the initial rate times the 100% plus the increase to the t power, which is, in this problem, every year. So y equals, the initial rate is 80,000 times 1 plus the percentage of 10%, but remember we have to use the decimal form, so 0.10 t, and then we will simplify that to 80,000, which is our initial, our y-intercept, 1.1 times t, and there is our equation, or our exponential growth function. Now we want to know what the attendance the 5th year of the festival is. So we'll write our equation. and that means t equals 5. We'll substitute that in. So in our calculator, when we type that in, what we're going to need to do is do that exponent. So really in that calculator function, you want to find the caret. It looks like this. It's a little button. Sometimes it's kind of hidden. You might have to hit the second key for it. And so you want to find that. So in the calculator, because this is multiply, we want to do our exponents first. So what we'll do is type in 1.1, then hit your caret, which means to the power of 5. So it's just a way to tell the calculator to go to the 5th power of that one. And then you're going to multiply, hit the times button and multiply it by 80,000. And that will get us 12,840.8. So that's funny. 0.8 of a person? So here we have to, yes, it's an increase, but it's a percentage increase. So here we have to do a little bit of rounding. So y, the number of people, are 12,841, because we'll round up, and we have to put our label in there, people, that would attend the 5th year. Problem number 2. The value of a car is $42,000. It loses 12% of its value every year. And that's what happens to cars. When you, they have a percentage of exponential, if it loses it, that would be an exponential decay. So my equation that I would use would be my initial A times 1 minus the rate, because it's a decay. We want to take that rate away for the number of years we have the car. So here's our initial A. So y equals $42,000 times 1 minus, now we have to make that into a decimal, so that would be 0.12. Now be careful when you simplify this, 1 minus this. Some people make a mistake and forget to regroup. So 1 minus 0.1 would be 90, and then we have to take 2 more away, so that would be 0.88 would be our multiplier times t. Then we bring our $42,000 down, and y equals 42,000 times 0.88 to the power of t. Now, what is the value of the car after 1 year, 5 years, 10 years, and 15 years? So after 1 year, we would use our equation, 42,000.88 to the power of 1. And when we use our calculator to multiply that out, we get 36,960. And that is dollars, because that's how much the car is worth the first year. In 5 years, we have y equals 42,000 times 0.88 to the 5th power. And that would, when we type that 0.88 caret, or to the power of 5, and then multiply it by 42,000, we get 22,164.74. Oh, yes, I need to put my dollar sign here to label it. After 10 years, our equation would be y equals 42,000.88 to the 10th power, and that would be, when we type that in the calculator, 0.88 to the power of 10, and then multiply it by the 42,000, we get 11,697.04099 as our decimal. So because it's money, it's dollars, we want to round it 967 to the nearest penny. So that would be 4 cents. $11,000. And then lastly, at 15 years, we'll do that same process, typing it into our calculator with the exponent of 15 would be 6,172.90. Now, when we think about this, what's happening is that exponential decay, and when we looked at those graphs, we can kind of think about what's happening in our graph here. So as the time is going, so our initial $42,000 is where the car is worth up here. That's our y-intercept. And then what's happening is that growth is going down, and then remember it's curving as it's getting closer and closer to zero. So if we think about every year coming down, as at the beginning it's much steeper in our growth or our decay here. So that means between the 0 year and the first year, it is the greatest decrease because it's an exponential decay. And then as we continue on, every year it's getting shallower and shallower. So this last between the 14th and 15th year, there's less depreciation of your car than in the first year. Our fifth example is determine if the function is an exponential growth or a decay. And then we want to identify the percent rate of change. So for these, we will look at the equation. So our first one is y equals 5, parentheses 1.07 to the t power. So in looking at this, I want to take a look at, oh, it's a growth or decay. So I need to rewrite it. I need to rethink this problem, and it's easier to rewrite it as that 100%. Now this one's going to be a plus 0.07. So remember, it's that 1 plus our rate. And so our rate is 0.07. So that would be translated into a 7%, 2 place values. And because it's increasing, it's a growth. Now, most people, when they see a growth, they identify it much easier because it's got the 1 here for the 100%. You can see the 100% and you can see your 7% right here. When we get to decay, it's a little bit trickier. So if we have our f of x equals 0.2 parentheses 0.98 to the t power. So if we take a look at, and a good thing to do is always kind of put it into that 1 plus or minus your rate. So we're going to put the 1 in here, and notice how it's not visible here, but it is there. But we're going to subtract a percentage to get to 98. So that would be 0.02. So really thinking about these two are equivalent inside our parentheses to get our rate, which is this one right here. We know it's decay because it's a subtraction to get it down below the 100%. So that would be a 2% decay. All right, example C, y equals 2, parentheses 0.64 t. So This I identify as a decay because it's less than 1. So I want to restructure that 1 minus. Now be careful here because a lot of people will put 46. And if you take 46 and add it to 64, you will get greater than 100%, which is wrong in our thinking. So we have to think about, you have to get to that 100% here. So how I think about it is get to 90 first, and then from 90 you can get to that other 10 to 100. So that would be 0.3 to get to 90, and then 6 more to get to 100. And just do a quick calculation back. 100, 9 plus 1 more is 100, or 10 plus 90 is 100%. So our percentage is 36%, and because it's subtraction, it's a decay. And our last one that is related to this is simple interest. So a lot of these formulas are very similar. They're just used in different places, so they look differently. But we can see that it is very similar to y equals a, parentheses, the 100% plus our rate of interest to the time, or x, as our independent variable. So the P here stands for the principal, and this is more of a banking, so they like to have their own variables. So the principal, which is our initial amount, and that is the 0, or the y-intercept, what you start with. We've got the 100%, and the R here is the annual interest rate. And the T stands for the time. And usually it's in years, because if it's annual, meaning yearly. Now, our example, we're going to be, let's say you got a gift of $1,000 when you were born. And your parents put it into a bank account at 5% interest, annual interest. So in our initial, or our equation, what we'll do is y equals, and our principal is $1,000. That's at the 0. 100% plus our rate. So we have to be careful here because this is a tricky one with the decimal. So remember to change the percent to a decimal. We move it over 2 places. So it would be 0.015 as a decimal to the power of t. And then we'll simplify that to 1,000 times 1.015 to the t power. Now, we kind of want to know some information. When you're 18 years old, how much would you have in the bank if you were to withdraw it then? If you left it there, though, how much would you have if you left it for 50 years? All right, so we will, very similar to what we did before, is our exponent of 18. So remember, this is definitely a calculator when we're using exponential growth a lot of times with the decimal of percentage rates. So when we type that into the calculator, we get a pretty big decimal. So we will round it to the nearest penny, which would be 1,307 and 34 cents after 18 years. So that would be 1.5% annually. So every year you accumulate a little bit more every year. And that would be about $300 after 18 years. And it doesn't seem like some people think, oh, that's not very much. Well, the first year, if you think about the first year, 1% times 1,000 would only be $10. So you made an interest of $15 that first year. So that $15 gets accumulated every year and with their simple interest. Now, after 50 years, we can use that and see how much that would be after 50 times of that interest. And when we type that calculator in, we're using the exponent of 50, we get $2,105.24. So it is much more significant after that many years of 50 years at that small interest or annual interest rate. You've more than doubled your money after that 50 years. And that is interest and growth and decay. So if we review looking at our formulas, they all have that same structure of y equals and then our initial amount or the y-intercept or the principal, and then our rate is either a increase with the plus or decrease with the minus, but they all start with that 100%, and then you either add or subtract your rate for the amount of time, which is your exponent, and that's what makes it the exponential growth or decay.